to express that fluid pressure is normal to a surface and based on the water, the weight of water at any depth. Actually, this is our main concept here that we can do all of our calculations based off of. And then we need to be able to calculate the pressure at any depth based on that weight of water, draw FBDs of rigid objects that are subject to hydrostatic fluid pressure that are going to allow us to solve for unknown forces, calculate the force caused by the hydrostatic fluid pressure on a rigid object and the support reactions, and then draw FBDs and calculate fluid pressure for rigid objects with vertical, horizontal, sloping, and curving surfaces. We're going to focus on vertical and horizontal today. And then after exam number 3, we'll do a lecture on sloping and curving surfaces subject to hydrostatic fluid pressure. Okay, just to give you an idea of where we're going, our homework, number 1, is just asking us to determine the magnitude of the hydrostatic force acting per meter length of the wall. They give us the density of water, and they give us the value of H there. They asked us 2 different types of questions in this, or really they're the same question, but they can ask us for 2 different things for our final answer. This is asking us per meter length of the wall. That's the into the page dimension. So that's a force in each meter that we have in that wall. And that makes sense when we have really long structures like this wall. Maybe it goes a mile into the page, or I guess this is an SI unit. So maybe it goes a kilometer into the page. Well, adding up the forces on that whole kilometer, you know, it might be like millions and millions of kilonewtons. It really doesn't make a lot of sense for us. And so it makes more sense for us to look at per meter length and say, how much force do we have in each meter of that wall right there? In other cases, we could be asked to find the total force, not the force per length. This one is asking us to find the magnitude of the hydrostatic force acting on gate AB, which has a width of 7 feet. So this goes into the page, 7 feet. And so finding the total force that's acting on this makes sense because it's only 7 feet into the page. And then this one also not super long dimensions. And so they're asking us for the total resultant forces that are acting on those walls of that fish tank. So let's jump in and let's start talking about a few things here. Actually, I might come back and look at these pictures, but we probably won't even come back and look at those pictures. So for our fluid pressure, the pressure is entirely based on what is called the unit weight. The unit weight of water. The unit weight is exactly the same thing as the specific weight. So specific weight, unit weight, exactly the same thing. I tend to see more often specific weight in like journal articles or more technical things like textbooks and stuff like that. But then unit weight, I see more often in practice, like the unit weight of something. The unit weight, we're going to call in US customary units, gamma. We're going to use the Greek letter gamma. And there's so many pounds per cubic foot. So when we're dealing with water, water has a unit weight. And I have a water jug here. And anybody have any idea? I have my luggage scale. Anybody have any ideas on how much this water jug will weigh if it's exactly 1 gallon of water right there? Anyone have 7 pounds? Yeah, about 8 pounds. Yeah, something like that. I'm showing like 8 pounds. Well, I don't know if you're going to be able to see that on the screen there. But it's, yeah, basically 8, right at about 8 pounds or so. And I can't remember the exact one, but we're talking about a cubic foot. So that gallon of water, that's different than a cubic foot. A cubic foot would be exactly 1 foot. And to give you an idea here, of how, how big a gallon is. Maybe it's like 6 inches by 6 inches or so. So anybody have any ideas? How much is like 1 foot by 1 foot by 1 foot into the page? So a cube, if you took like a fish tank that was exactly 1 by 1 by 1 and you filled it full of water, anybody have any ideas how much that weighs for fresh water? Because our pressure, 65, that's really close. 62.4 pounds per cubic foot. And so what that's saying is that a 1 foot by 1 foot by 1 foot cube of water has a weight equal to 62.4 pounds. If we go into SI, so that's our 62.4. In SI, remember our base unit is kilograms. So we don't start with a unit weight, we start with density. Rho is our density, and for water, it's 1,000 kilograms per cubic meter. Kind of interesting how water is exactly 1,000 kilograms per meter cubed, isn't it? So water has a specific gravity equal to 1, doesn't it? Okay, so we're not going to really get into specific gravity, but our density is 1,000. We can still calculate gamma in SI units. It would be rho times G. So 1,000 kilograms per cubic meter times 9.81 meters per second squared. That means our gamma is going to be 9.81 kilonewtons per cubic meter. So we still have a gamma, but remember that in SI, our base unit is kilograms, is mass. And so we start with the density, while in US customary, our base unit is pounds. And so we don't really think about the density of water. Let's look at now calculating the pressure at any depth. So if we take the phreatic surface, so this is like the water surface right here, and we denote the water surface, like if I didn't have the blue color or something like that, an upside down triangle with 3 lines of decreasing length. That's our symbol to say, hey, here's the water surface. There's the top of our water right there. And let's take a field trip. Let's all go to the rec center and we're going to go swimming. And so here we are at the rec center. We're swimming below the surface of the water. And I imagine most of you have been swimming before, whether it's in a swimming pool. There's probably some people that maybe have not, but we develop this pressure. When we go down under the water, we start to feel the pressure in our ears. And if that pressure that we're feeling, that's the pressure that we're going to calculate right here. So let's say we want to calculate the pressure right there on the top of our head. And let's say we're at a depth here of H equal to 10 feet. And so what is our pressure right there at point A? Well, it's just based on the weight of water and how much water we have above our head. So it would be gamma times H if we're doing this in US customary units. And so that's going to be our pressure at A is going to be 62.4 pounds per cubic foot times 10 feet. And let's take a look at the units here. I'm going to keep track of our units. We're going to end up with PA equal to 624 pounds per square foot, right? The cubic foot on the bottom cancels out with that 10 feet right there. And so we end up with 624 pounds per square foot. That sounds like a lot of pressure, doesn't it? 624 pounds. You can swim down to 10 feet, though. You definitely, if you're not used to it, you will feel it hurting in your ears. You can build up your, you can kind of somehow relieve the pressure by, blowing through, plugging your nose and blowing and kind of creating a back pressure in there. But to give us an idea of like what 624 pounds per square foot means, how about if we converted this to PSI? In pounds per, in PSI, this is 4.33 pounds per square inch. So PSI is pounds per square inch. So that just gives us an idea of what that 624 really means. So really at 10 feet, we have about 4.33 pounds per square inch, or PSI, that we're feeling there. And to relate that to something that we're familiar with, anybody know what's kind of a typical pressure in a tire, whether it's a bike tire or a car tire? Like kind of what's kind of a nice number in that? Yeah, some bikes are like road bikes are like 80 psi. I think in my old mountain bike that I have, I think it's like 30 psi. In my vehicle, yeah, 36 psi, right? So that just gives you an idea. We're about a sixth or a seventh of the way at 10 feet of depth. We're about a sixth of the way to a like 36 psi, or seventh of the way to a 36 psi for a vehicle, right? So that's 10 feet. Now, how about in SI? Let's do these same calculations in SI now. So in SI, H equal to 10 feet is 3.05 meters. And you all are not going to have to do any converting between US customary and SI units. I'm just kind of relating this all to one another. And for our pressure at A in SI, be rho times G times H. Well, we know that rho times G is 9.81 kilonewtons per cubic meter. H is 3.05 meters. And so we're going to end up with a value of 29.92 kilonewtons per square meter. We are not going to be working with flow rates at all, Kalev. That's for fluid mechanics. Can do some open channel flow in fluid mechanics, and for some cubic feet per second, some river flow data. Those rivers should be starting to come up pretty soon, huh? I've seen, we'll talk more about fluid pressure on after the exam, and we'll talk a little. Well, I'll have an example where we talk about the flow of something, but it's not really related to what we're doing. Okay, so all three of these numbers, though, 29.92, 4.33, and 624. That, to us, if we were in the swimming pool, we would feel exactly the same thing. They're just three different numbers that represent the same thing. Okay, a key concept. So that's, if we can calculate the pressure at any point, and all it is based on the depth of water at that point, then the other thing that we need to know is that the pressure always acts normal to a surface. With those two things, we can calculate the pressure in pretty much any shape and any type of structure. Let me draw a little picture here of pressure always acts normal to a surface. If we had our phreatic surface or the water surface here, and you'll see a lot of times a shorthand for this upside down triangle is to just do a squiggly below it like that. So instead of doing the 3 lines of descending length, You just show it a squiggly right there. And then let's take like, what if we had like some thing that was shaped like this? You know, it kind of looks like a potato or a rock or something. Well, right here at this point, our pressure would be normal to that surface point right there. If we came over here, it would be normal to that. And if it's a little bit deeper, then we're going to get a little bit more pressure on it. Or right here, it's going to be normal to that surface right there. So we're seeing two things, right? Our pressure increases with depth, and it's always going to act normal to whatever surface we have there. It's a fluid, it can change shape, and so the pressure acts always normal to that surface. There is no fluid pressure perpendicular to the surface. In fluid flow, yes, but hydrostatic, there's nothing perpendicular to the surface there. Okay, so the next thing, let's take a look at now related to the homework problems and to one of the main things when we have fluid pressure in a structure, we're trying to figure out how much force is exerted on that. And so let's look at the pressure distribution. On a vertical wall. So I'm going to leave a bunch of room up in this region right here to draw a three-dimensional view of this, but I'm going to start with 2D down here. So let's say we have this wall right here, and maybe this is our wall at the swimming pool, right? We're still in the swimming pool at the rec center, and we have this wall here. And let's say the wall has a height of 10 feet, just to kind of make our numbers easy for calculating. So let's say our H is equal to 10 feet right there. And we'll put the water surface all the way at the top of that wall right there. So there's our phreatic surface. And I'm going to leave some room just to the right of the wall, right in here, to draw the pressure distribution that's acting on that wall. So we're going to end up with our pressure distribution right here at the surface. What's our pressure at that spot right there? At the very top of the surface, it's 0, right? And this is, yeah, and we're talking, you know, we're talking gauge pressure here. We're not talking like the absolute pressure. We're not taking into account atmospheric pressure or anything like that. We're just talking about what is the pressure in the fluid, you know, neglecting all the atmosphere pressure stuff. So then what happens as we go deeper and deeper, like if I go 1 foot below, well, if I'm 1 foot below, what's my pressure? Isn't it 1 times 62.4? And then if I go 2 feet below, it's 2 times 62.4, and then 3 times 62.4. So we end up with a linear pressure distribution, which ends up giving us a triangle. And so what we see on this wall here is we see a triangular pressure distribution, where if we can calculate the pressure down here, we can call this point A again. Our pressure at A is going to be equal to gamma times H, or what we found before, 624 pounds per square foot, since we're at a 10-foot depth there. Now, let's do the three-dimensional part of this, because that's our pressure at that point, but we can simplify these problems down to 2 dimensions, but it's nice for us to visualize what's going on in that 3rd dimension. So let's draw the rest of this wall here on our swimming pool. So there's our swimming pool wall, goes like that. And so we'll draw the whole wall here, and we could provide a length, a dimension into the page here. So this has some, we'll call it, how about we call it B? So we get some distance into the page there. and we'll call that distance B. Well, that pressure is constant into the page there because the water depth, we'll say the water depth back here, it's all the same. So our water depth here, right? Usually the water depth doesn't change. Water is flat. And so our depth of water is going to stay the same. Now, if the pool is getting deeper as we go into the page, then that's a different scenario. We're really not going to worry about in this class. So our pressure distribution then back here would be exactly the same. We would have, our pressure would go back like this. We would have a PA that is right back there. And then we can connect those two. So we kind of end up with this pressure wedge that's acting on our wall there. So how do we go from, we want to go from basically H all the way to a resultant force. Well, there's 3 steps that we can do to do this. Number one, we're going to calculate the P at A, and that's equal to gamma times H. The second thing that we're going to do is we are actually going to find a distributed load from that pressure distribution. W is a distributed load. And it's equal to the area of the P distribution. So for us, that's going to be 1/2 times PA times H. So we're finding the area of our red triangles. So the P distribution, those are the red triangles. So we basically found this area right here. What that is going to give us, that W that it's going to give us, is going to act at the centroid of our P distribution. And it's going to go back into the page like that. So there is W. And it's a rectangular distributed load. So that distance right here, from there to there, that's our distributed load, W. In the homework problems that ask you to stop at the force per meter length of the wall, we are done there with step number 2. Let's go ahead and figure out our W for this problem. So 1/2 of PA is 624 pounds per square foot times, what do we need to multiply it by? I'll pick somebody from the front row. How about Luke? Luke, you're in the front row today. Luke Giffen.
Repeat that, please.
Yeah, what do I need? I got one more term here. What do I need to multiply it by? 1/2 620.
Times the distance B.
Nope, not times distance B. We're finding the area of our red triangle. So isn't that
times the height? Sorry, yeah.
Times the height. Yes, thank you. No, and that's nothing. That's why I ask those questions, right? Is not necessarily always to be like, oh, do you know the answer? But to just for everybody to stop and think about that so it can soak in. Thank you, Luke. Okay, so we're going to end up with 3,120 pounds per foot. That right there is per foot into the page. So this is that B is that into the page dimension. So this is into the page right there. So 3,120 pounds per foot. Now, if B is really big, and maybe in our swimming pool, I think it's a 25-yard swimming pool. So B could be 75 feet. we could figure out how much force is acting on that whole 75 feet. But actually, if we were designing the concrete and the rebar that goes in that concrete to hold the moment that this is going to create in that swimming pool wall, do you think it'd be good for us to know the total force that's acting on it, or maybe how many pounds we get per foot? Because the rebar is probably going to be figured out in each foot, right? How much rebar do we need in each foot of the wall? So for design, it might make sense to stop at that 3,120 pounds per foot for that W, that uniformly distributed load that's right there. And then our third step here is we can calculate our force, and F is going to be equal to W times that distance into the page times B. Let's say B is equal to 75 feet. And so our F would be 3,120 pounds per foot times 75 feet. We're going to end up with, I need my calculator. Where'd my calculator go? I don't think I did this calculation here. So 3,120 times 75, 234,000 pounds that's acting on that whole swimming pool wall, assuming that it's exactly 10 feet deep for the whole length of that wall. So 234,000 pounds, that may not tell us very much about how we need to design this thing. And then also, where does that F act? Well, just like we have this uniform distributed load here, so wouldn't F act exactly halfway from left to right here? So let me go, maybe there's our center line of the wall there. So we can say this is B over 2 and a B over 2. And so that is where our force is going to act. So right there at B over 2 and B over 2. Oh, and then also I just realized I did not label where the distributed load and F are located. Well, they're both going to be, if we go from the base of the wall here, they're going to be located at 1/3 of H. Or if we can show it over here, we can show it at 1/3 of H right there as well. Oops, let me go back so you can still see that, since I just added some stuff to that picture. So when we're doing fluid pressure, follow those 3 steps. Find your pressure, then convert your pressure into a W, and then you can convert your W into an F. It's just a really nice way of doing things that'll work for all of our problems in statics. Okay, but now you don't need to draw the 3-dimensional view every time. This can always, you know, we can always just use a 2D picture because nothing is changing in that 3rd dimension. So really, this is how I would draw, this is how we should draw that in the future. Here's our pressure distribution, our pressure down here at A, our W. What color did I use for W? I think I used purple. Our W is going to act right here. And this is also the same location as the force as well, because they're both at 1/3 of whatever our height of the wall is equal to. All right, so we really don't need to draw that 3-dimensional view. Nothing is changing into the page for us. I can add some more arrows on our pressure distribution right there. Okay. And let me make this is W and F are in that same spot. Okay, let's look at an example here. We have a wall with a gate in it. And this gate is down here. It goes from point A right here, and then there's a point B that's down here. We have our water surface is there. We're given that this dimension, we'll go into SI units, is 2 meters. And then the bottom of the gate is at 3 meters right there. And we could say that there's a floor or something. Actually, no, wait, there's not a floor right there. The wall continues going down like this and then eventually gets to the floor right there. Our gate is gate AB is 1.5 meters wide into the page. It's 3 meters tall and 1.5 meters tall. If we looked at an elevation view, so this is the one up here is really a section view. Our elevation view would look like this. We have this wall, and then we have a gate that looks something like this. So this is our 1.5 meters by 3 meters. And so point A is up here and point B is down here. So we're looking straight on at the wall, the elevation of the wall. It would be a 1.5 meters into the page and then 3 meters up and down. Or 1.5 meters left to right and 3 meters up and down. And what we would like to find for this gate is the magnitude and locations of the resultant forces. We're really, we could find the support reactions at A and B if A were like a pin and B exerted a horizontal force or something like that. But we're going to focus on just finding the hydrostatic fluid pressure part of this example. So for our solution, let's start by drawing an FBD. We have point A is right here, and then let's draw a little bit below that. We have a point B is right there. Our phreatic surface is here. And it's not exactly an FBD. This is really more of just drawing the pressure distribution. So our pressure we know is going to start at 0 here, and it's going to be linearly increasing as we go with depth. Well, we are specifically interested with the pressure distribution that's only acting on the gate there. So we have really what we end up with is a trapezoidal pressure distribution with a PA and a PB. Let's add some dimensions to this. We know that's a distance of 2 meters, and this is a distance of 3 meters. So let's follow our 3 steps. So we have our first, we drew our pressure distribution. Next, we have our 3 steps. And so that was basically, we go from P to W to F. And it's always going to work for us. So we have a gate now, right? It's a trapezoid, but this process is still going to give us all the data we need in a nice, efficient method. So what's the pressure at A? It would be equal to, what's the terms? What terms should I write down for calculating the pressure at A? Who else from the front row is here today? Let's see, we're E and H here, E through H. That would also Let's see. Oh, Spencer Ayers.
Could you repeat that again?
Yeah, what term should I write down for PA? What's my equation I should write here?
It should be the area of the triangle, right?
Not for pressure, that's for W.
Oh.
Almost there.
When gamma times the height.
Right, gamma times, exactly. Gamma times height. I'm going to write it just a little different since we're in SI. Rho times G, which is gamma, times H. So yeah, same exact thing. We know that rho times G is the same thing as gamma. For SI units though, remember we start with this 1,000 kilograms per cubic meter times 9.81 meters per second squared, and then times our height, which at A is 2 meters. And so we're going to end up, when we plug this in here, we're going to end up with 19.62, and I'm going to convert it into kilonewtons per square meter. We could do the same thing for PB. It's going to be rho times G times H for that one. And so really 9.81 kilonewtons per cubic meter. I combine the rho and the G there, times H. Which H should I use though? Let's see, E to H. Everybody, all the E to H's are hiding here. How about anyone? What do you all think? 5, yes, right. It's all the way to the top. Don't use the 3 meters, use the 5 meters right there. And so we're going to end up with a value here of 49.05 kilonewtons per square meter. Okay, now we can do our W's. And because we have a trapezoid, let's break our W's into a W1 and a W2. So W1 would be for the triangle here, or actually, let's see, what did I do? And I called that W2. So for the triangle right there, and I'll draw it right there, we'll call that W2. And then W1 would be for the rectangle. So W1 would be acting right there. And we can find W1 is just going to be equal to the area of the rectangle. And we are going to get a basically, isn't it just going to be PA times 3 meters? And so we'll end up with 19.62 kilonewtons per square meter. If you're getting lost too in fluid pressure, keep track of those units. And if your units work out, a lot of times that means that you're following the correct process. So we see a meter here in the 3 meters over a meter squared. So we're going to end up with W1 being a 58.86 kilonewtons per meter. And remember, the way we're going to do this, that is always going to be per M into the page. Remember, that's a uniform distributed load that's going all the way into the page across that 1.5 meter distance there. And then we can do W2. W2 is going to be the area of the triangle. And so that's going to be 1/2 times the height of the triangle, which is PB minus PA, times 3 meters. And we're going to end up, when we plug all this stuff in, we're going to end up finding a 44.15 kilonewtons per meter. And then our last step here is going to be, we can find F1 is going to be W1 times 1.5 meters. And remember, this is into the page. And then F2 would be W2. Oh wait, let's calculate F1 first before we go into F2. So F1 is going to be, let's see, W1 was 58.86 kilonewtons per meter times 1.5 meters. And so we're going to end up with 88.29 kilonewtons. And then F2 would be W2 times that 1.5 meters. And this one is going to give us 66.23 kilonewtons. So we followed those 3 steps, didn't we? We did number 1 was that stuff there. And then number 2 is all of our W stuff. And then number 3 is all the F stuff. If they ask us to find the force per meter, well, we would stop at W. But since they ask us to find the total resultant forces that are acting on there, we stop there. Now, so what we have at this point is we have this gate from A to B, and we know that there is an F1 that's acting right here and an F2 that's acting right there. If we wanted to say, find the reactions at A, we know that this is one, we know where F1 is, it's at 1.5 meters. We know that F2 is down here at 2/3 of our 3 meters, or at 2 meters right there. So now that we have our F1 and our F2, we can do all the other things that we've done for statics. We can take moments, we can sum forces, whatever we're looking for in our particular problem. We're back to a familiar scenario with forces, and so we can take moments. We could also combine those forces into one equivalent force, right? But we don't really need to. If we want to sum moments at A, do we need an FR, a weighted average between F1 and F2? No, we don't. We can sum moments at A by having an F1 and F2. And I see a question in the chat here. Why did I multiply W2 by 1.5? Those are both the distances into the page. This 1.5 here, that is also 1.5 meters into the page right there. So our W's are always going to be per meter into the page. I can annotate that too. That's per meter into the page right there as well. And that was that 1.5. If I zoom back out here, that 1.5, that's this distance here. That's all I'm over in the bottom left corner, right? That's our 1.5 meters. That's the gate. AB is 1.5 meters wide into the page. Any other questions?